Hello. So, today we're going to be talking about the latent heat experiment. So, the goal of this experiment is to simulate the latent heat L of a substance in relation to a change in mass using liquid nitrogen. So, we're going to be first measuring the rate of vaporization based on a change in mass over time, and then using that rate of vaporization, we're going to be trying to measure it at different electrical powers. Then we're going to set up another plot which is going to compare the different rates of vaporization with different amounts of power used from batteries. From there, we can compute the latent heat. With these formulas here, we're able to find the latent heat. This is going to be based on the inverse of the slope. And then we're going to be trying to find the heat leakage into the environment based on the intercept of that same slope. So, first we'll talk a little bit about the illustration here. So this is kind of a illustration that I drew out myself and set up to sort of simulate what the experiment's going to be. So, first, we'll basically have a cup here. This cup will be filled with liquid nitrogen, and these are going to be resistors, which are being charged by a battery, managed by a key. It's going to have a power output. It's going to have different things that'll measure the current and measure the voltage. And then we'll have a timer, and then we'll have a scale to measure the mass. So, this is a circuit diagram setup of this experiment here. So, now for a little bit of background and sort of the theory that goes along with this. So, what this is based off of is the temperature of a material remaining constant while in phase change. So basically, with how latent heat works is that the temperature itself will remain constant while it is undergoing a phase change. And what this will mean is that as the heat is being lost or gained, it will not change in temperature. It is simply the substance itself is changing from being, let's say, a solid to a liquid, or to a liquid to a gas, or vice versa. And so these different types of latent heats are basically different processes. So in general, latent heat is the difference in internal energy during a phase change. When it's in a freezing process, it's latent heat of fusion. During vaporization, it's latent heat of vaporization. With this experiment, we're going to be looking at latent heat of vaporization. All substances have their own latent heats. Ln2, which is liquid nitrogen, is just simply easy to measure the latent heat of due to it being a noble gas. It's already at a super cold temperature, so we can simply put in a certain amount of power from a battery to put this back into being a gas. So that's the importance of it vaporizing at a very low temperature. It makes it easy to see the difference when you're changing its mass. And so by applying a higher power, you can increase the rate of R, but the latent heat of the substance will always remain the same. So, what we can see here is there were 6 trials done. And in these 6 trials, what we can compare is the time. So we measured this in minutes, in 1 minute intervals. And we measured it in 1 minute intervals by setting it up as seconds, because seconds allows us to get good estimates based on the time period of seconds. So anyways, we basically measured it all the way up to about 15 minutes, if I did my math correctly. And so from here, what we can see, based on all of these rates of change, are that the mass is, in general, decreasing. It is just simply decreasing with each and every trial. And this can be seen also within the graphs. Within each of these graphs, what we can notice is that there is a linear trend going downwards. So as it changes in time, we'll see that there's less mass. It's losing mass as it has power applied to it from the battery. And that's what we can see with all of these trend lines. But as you might notice, some of them are higher than others, which allows us to see and compare each of these graphs. So this is where we're getting our rate of vaporization from. We're getting it from these trend lines. So then what we can do is we take the powers that we use from the battery and compare them to each of the slopes that we get. So here we have each of the slopes that we got, and now we can compare it to the respective power that's used. So with this, what we can find is that we now get a new plot. With this plot, what we can see is the evaporation rate versus the power. And so by extracting the slope of the graph, we can find the latent heat. And from the intercept, we can find the heat leakage, because this is basically the extra heat that is getting extracted. And that's what the intercept will show. That's why it's not really a perfect line here. So through some of the calculations, we basically are able to extract three formulas. So the first formula that we can extract, let me correct myself. There are two formulas we can extract, and one of them is the latent heat formula. And we find this by doing the inverse of the slope gotten from this previous graph here. By doing the inverse, we are able to compute the latent heat. And since the latent heat is constant, we can get a best guesstimate of the latent heat based on these 6 trials. If we did more trials, we would be able to get a better estimate of what it is. But since we only did 6, the best estimate we can get is what ends up being gotten here when computed. So these are the formulas. So we originally go off of the formula of the latent heat and the rate of vaporization being equal to the power plus the heat leakage power. And then we have to compare it to a slope equation, since we're using a slope here. So what we have to do is we have to rearrange the variables so that we can extract these formulas. This formula right here is simply the error in the slope. And what it allows us to see is simply the error in the latent heat. So once we have all of these formulas, we can then start computing. We can start finding what each of these values are. So what we find for the latent heat is that it's about 193.424 joules per gram. What we find for the error in L is that it's about plus or minus 26.18 joules per gram. And now for the error propagation, which is also the heat leakage, which is also P0, we find that P0 is 15.667 watts. Now, something that's kind of interesting about this number leads to some of the observations that we can see. As described before, the temperature stays constant throughout the experiments due to its phase change. When it's undergoing the phase change, it is maintaining a constant temperature. We also notice, as said before, that the mass decreased faster when more power was added. That's what we were able to see with the steeper slopes. And then also the other thing we were able to see, and this was based on the table measuring the latent heat, or measuring the power versus the evaporation rate, is that there's a bit of an error. So that's another observation that we can see. So this leads to a bit of the results and the conclusions based on these observations. And some results and conclusions that can be drawn from it is that what we'll notice is when we were computing that error propagation, which was also the heat leakage, it was around 15 volts. And what this basically tells us is that the heat from the environment is actually contributing more than the battery power itself because it is a higher wattage. This is supposed to be watts. I don't know why I said volts here. There we go. Perfect. So, here, let me fix it here. There we go. I don't know why I said that there. Anyways, so what this basically tells us is that it's higher than the resistor power of the battery, which, as we can see, the highest value here was 8.84 watts, or joules per second. Whereas the result that we got here is 15.6, so it's higher. It's higher by about twice as much. So from there, what we can sort of conclude is that while the battery power has an effect, the main source of energy causing most of the mass to be lost is the heat from the environment. And basically, what we can also see is that another thing that may affect the slope is that as the temperature of the room, as the room temperature gradually changes over time, there may not be the same slope because the temperature may be higher or lower. Let's say the sun starts to go down and the temperature of the room starts to cool down. There's no longer as much heat that is taking energy away from the liquid nitrogen, so it's lower. Or the room could be higher in temperature, and what we can find from that is that it is taking more. So it'll vary depending upon the time of day. Or I guess, in this case, the room temperature, whatever the room temperature is. And that's why it's not perfectly linear. And so I figured it would be nice to provide an additional example. So as said before, all substances basically undergo a latent heat change. And water is a really good example of this as well. And so something that's kind of interesting is that if you make water move around, like let's say you have like a big bucket of water. If you want that to take longer to undergo a latent heat process for whatever reason, maybe you want the water to be colder than 32 degrees Fahrenheit or 0 degrees Celsius, you can move it around, add ice, or even add salt to make it so that the water will be colder. It'll be harder for it to undergo a phase change of freezing. This is just the case of phase change of freezing. But and the same goes with rivers. It takes a much colder temperature of water with rivers in particular to undergo the transformation with latent heat. It takes a lot longer because it's moving water. And so that's what makes it more difficult, let's say, for a river to start freezing. So I thought that would be a nice little example as well. So I figured let's do a quick summary and recap. So basically what we set up here was six mass versus time graphs so that we could see the linear rate of decrease in all 6 trials. Then from there, we can notice that some of the slopes drop a bit faster than others due to different amounts of power going into them. From this, we can compare the 6 slopes with the corresponding power outputs used. We can get a slope and an intercept for this data. And then from there, we can do out the calculations and draw the conclusions. And that's what allows us to see the process of latent heat. We're able to gather a latent heat, and we are even able to draw the conclusion that there's more energy in this particular situation that is involved with the room temperature. So, that is my presentation. Thank you for listening, and have a good evening or morning, depending on where it is for you.